Hi, I'm Granö from Aalto University, and I'm going to talk about how the pre-stimulus phase of spontaneous cortical oscillations affect signal propagation after a TMS pulse. So I will first go through some background for this phenomenon and then delve into the methods and results of this study. When you stimulate a cortical region with transcranial magnetic stimulation, the initially local responses first spread within 5 to 10 milliseconds to adjacent cortical areas and then to contralateral homologous areas after about 20 milliseconds. And this has at least been shown for stimulation of the primary motor cortex, shown in this upper row here, and the occipital cortex, shown in the bottom row. And this is shown with TMS combined with electroencephalography, so EEG. And the EEG signal can be taken to the source space to more accurately localize the activity. What this means is that the TMS-induced activity propagates to distant cortical areas from the stimulated region, and also this can be assessed with EEG. And individual responses to TMS are highly variable, both within the subject, but especially between subjects. And this is partly because the responses are modulated by the prevailing brain state during stimulation. So an example of this is the breakdown of cortical affective connectivity during sleep. TMS-evoked responses in awake subjects produce these high-frequency complex responses that spread to distant cortical regions, while TMS-evoked responses in subjects in non-REM sleep stay local and are of low complexity and quickly die down. And TMS-evoked responses are also modulated by spontaneous cortical oscillations. So both phase and power of the oscillations, as you can see with EEG, has been shown to modulate many aspects of the TMS-evoked responses. So as an example, the phase of the mu rhythm at the primary motor cortex predicts corticospinal responses to TMS, or more specifically, stimulation during the negative peak of the oscillations results in bigger motor potentials and stimulation at the positive peaks of the oscillations. And in this study, we were interested in how the phase of the cortical oscillations affects TMS-induced signal propagation, meaning how stimulation during different local cortical excitability states might affect where the TMS-induced activity spreads after the TMS pulse. And the hypothesis is that the signal will spread to different distant cortical regions from the stimulated site, depending on the pre-stimulus phase of the mu and or the beta rhythms at the stimulation site. So to investigate this, TMS was applied to 2 cortical areas for 3 subjects, to the primary motor cortex, so M1 at the abductor pollicis brevis hotspot on the left hemisphere, and to right pre-supplementary motor areas, so pre-SMA. And the TMS-evoked responses were measured with a 60-channel NextSTIM EEG system. The stimulation parameters were fine-tuned to minimize muscle contractions, to keep the data as clean as possible, while keeping the early evoked responses at peak-to-peak amplitude of about 6 to 10 microvolts, and 250 pulses were given to each area. And after pre-processing of the data, the phase of the oscillations of the mu rhythm, so 7 to 13 hertz, and the beta rhythm, so 13 to 30 hertz, at the stimulated site were evaluated by using a narrowband Hilbert transform approach, where the pre-stimulus data segment is first padded with 500 points. Then you apply a Butterworth filter to this data and then a Hilbert transform to obtain the instantaneous phase exactly before the TMS pulse. And the trials were after this divided into 2 classes based on the phase, into a positive phase class and a negative phase class. And this figure here illustrates that if a TMS pulse had been given in the blue time window, this would have gone into the negative phase class, while a TMS pulse at the red time window would have made it go into the positive phase class. And this data here is otherwise. It's resting state EEG data from one channel to illustrate this. And because the trials are sorted according to phase, some background oscillatory neural noise might still be present in the class average, which means that there could be a causal relationship between the responses and the phase due to the ongoing oscillations. To make sure any possible differences between the classes don't stem from this, pseudo trials were created from the EEG data between the TMS pulses. Then these trials were sorted according to phase, and their mean responses were subtracted from the actual trials. Then cluster-based statistics was used to assess the differences between the two classes. So for those not familiar with this method, it's used for solving the multiple comparisons problem, which is often a problem with EEG data, by clustering. So first you use a statistical test of choice on all data points. So you use an independent sample t-test as this initial test statistic. Then you cluster together the initially, so at this point, significant data points based on temporal and spatial adjacency, and add all the test statistics within each cluster to form a cluster level statistic. Then permutational tests are performed by reassigning the trials randomly into new classes a big number of times. And then the clusters are calculated for these new random classes. And you gather the cluster level values from these into a distribution. You can compare your original clusters with these to be able to assign p-values to the original clusters. And after setting a threshold for the p-values, you're left with only statistically significant clusters. So for the results, of the high variability between the subjects, as significant clusters were found at different time windows and scope areas for different subjects. And the mu rhythm seemed to play a big role at the stimulation of the primary motor cortex, as more differences in the TMS about EEG potentials we found for the mu rhythm than for the beta rhythm, while both rhythms seem to play an about equally big role of the stimulation of pre-SMA. So here's an example of the class differences for one subject after M1 stimulation for the mu rhythm. So the upper row shows when and where significant differences were found for the two classes, while the second and third rows show the average topographies of the positive phase class and for the negative phase class. And the blue areas show that the negative phase trials have significantly larger EEG amplitudes than the positive phase trials. Yellow areas indicate that positive phase trials have significantly larger EEG amplitudes than the negative phase trials. And this you can also see from the topographies. So for example, let's get this blue area here. So the negative phase class have this strong red area that is either a lot weaker in the positive phase trials or possibly completely missing. And the topographies give a rough estimation of the locations of the active sources in the brain. And so these differences between the classes indicate that different brain areas are active at these times. So therefore, this indicates that the TMS-induced activity has spread from the stimulated area to different cortical areas, depending on the phase. So this seems to mean that the pre-stimulus phase modulates TMS-induced signal propagation, which means that the stimulated neuronal population prefers different connections based on the pre-stimulus local excitability. So there's a possible role of cortical oscillations in effective connectivity, which means that the cortical oscillations have extended roles past that of local excitability, and this also provides general further evidence on the influence of spontaneous cortical oscillations in shaping the neural responses to a TMS pulse. However, more investigation is still needed, so we need more data and more subjects to quantify the results and to understand how the pre-stimulus brain activity shapes the cortical responses to TMS. And we should also likely adopt some new methodology So, for example, it's possible that the correction method for the background neural activity didn't perfectly remove this oscillatory noise before the statistical comparison of the negative and positive phase classes. Instead, the TMS rails could, for example, be compared with resting state data, so we're sure that we're looking at activity that's evoked by TMS, or use a more reliable method for removing the background oscillatory noise, such as signal space projection source-informed reconstruction approach, so SSP-SIR for short. These results still give new insights into the role of cortical oscillations, and it's especially important for future closed-loop and brain state-dependent TMS paradigms, which reduce variability in studying cortical networks. And the possible future closed-loop stimulation paradigms will be vital for individualization of clinical applications of TMS, as well as for making treatments more efficient. And at the same time, this also opens up many new avenues of both clinical and basic research for further studying where exactly the signal propagates, what modulates this on a neural level, and more rhythms and brain areas could be studied as well. I want to thank especially my supervisors, Pantelis Digomis and Tuomas Mutanen, and my other collaborators, Professor Mario Sanova, Aina Tervo, Victor Sousa, Jaakko Nieminen, and Professor Risto Ilmaniemi for all their contributions to this study. Thank you for your attention, and I will see you in the discussions.